Okay, this is the fifth lecture, or the fifth video in a series on single agent search. And in the last lecture, in the last video, we were looking at heuristics and the definition of heuristics and things related to that. And now we're going to look at how we can combine heuristics into best first search algorithms and look at their properties. And so we're going to look at two algorithms today. The first thing we're going to look at is what's called pure heuristic search. And a more common name for this, or another common name for this, depending on the field that you're in, would be greedy best first search. And after we look at that, we won't spend too much time on this algorithm. Then we're going to go ahead and look at A star. Okay, so if we recall from before, when we were using a best first search algorithm, we had a guiding function, which was going to be f. And for these, we're going to define f of an n, so what is the priority for some node n, to be equal to h of n, or implicitly h of n to the goal. And so as a very simple algorithm, it's very greedy. It looks only at the heuristic. And if we saw before that Dijkstra's algorithm, in looking at the search, this is in the last video, the Dijkstra's algorithm basically searches out in all directions uniformly. And so we can want to add something like a heuristic to guide the search. So if we decide to guide the search just directly by using h of n, then we can start to look at the properties here. And so the question is, first, is it complete? Meaning, will it find a solution if a solution exists? And it is complete on finite graphs. This isn't very hard to show on a finite graph, and if a solution exists, right? So if I have a graph and there's a solution somewhere and I just start expanding nodes, eventually I'll expand all of them. And so that's going to get me to the goal. And then we can ask some other properties, sort of the more interesting properties. Is it going to be optimal? It's fairly easy to show that this would not be optimal. We can create many examples. And here, even if the heuristic is admissible, inadmissible, whatever we do, it's fairly easy to show that it's not optimal. And then the space and time really are going to depend on the problem. But in the worst case, we could be looking at the entire problem and find the goal last. So you could imagine something like a state space where the heuristic is 0 everywhere, except the neighbors of the goal. Let the neighbors of the goal have a heuristic of 1, and then the goal has a heuristic of 0. And so then we would expand every state in the state space except the neighbor of the goal. We would then expand the neighbor of the goal and then the goal itself. We might save 1 or 2 neighbors of the goal overall, but in general, we might have to expand the entire state space. So that being said, although in the worst case, it's really bad, so the full graph here. In practice, it may not be so bad. And so if you look at planning, programs that compete in the planning competition and things like that, they very often use greedy best first search as the guidance for their search. And anyway, so this is something that you would use if you are not looking for a bounded solution. You just are, you want to find the best solution that you can as quickly as possible. And on really hard problems, then that might be all that you can afford to do. But what we'd like to do is we'd like to upgrade, and we'd like to upgrade to something that's going to work a little bit better. So if we think about Dijkstra's algorithm, then what did that do? That looked only at the cost so far, which was the G cost. And we look at pure heuristic search or greedy best first search, then we're only looking at the H cost. And what we'd really like to do is look at A star, which is going to balance both of these. So A star is going to use f of n is equal to G of n plus h of n. And what we see here is that g of n is the cost so far, h of n is the cost so far, and so this is an estimate of the solution length. And this makes a lot of sense, right? We should, if we want to find a path and we want to know, like, is this node going to help us find a path to the goal? We could think about what would the cost of a path from the start to this node to the goal, what would the cost of that path be? And so that's the estimate that is being calculated here. And so now we can ask the same sort of questions that we were asking before. So we can ask, is it optimal? and is it complete? So it's complete is fairly straightforward. Again, in fact, any best first search algorithm is going to be complete. Particularly if we don't re-expand nodes, it's fairly easy to show that on a finite graph will always be complete. If we re-expand nodes, but only re-expand them when we get a shorter path, and it's a finite graph, then again, there's only a finite number of paths that we have through that graph. There could be an exponential, but it's a number of paths, but they're still finite. So if we have a best first search, and then in general, the best first search, we're always going to we're always going to eventually find a path to the goal. So yes, it's complete. But what's more interesting here is optimal. And so we're going to look at different properties here. In this lecture or in this video, I'm going to focus primarily on the question of if we have an admissible heuristic. And we'll talk more later about what happens if we have sorry, did I say that wrong? Okay, not an admissible, not just an admissible, but actually also a consistent. Sorry. So a consistent and an admissible heuristic, since consistent heuristics with a h of 0 at the goal is also going to be admissible. But we'll look at a consistent. I'll mention very briefly what happens with an inconsistent heuristic, and then in a later video we'll be analyzing that case. Okay, and so what we want to do is we want to analyze what A star does. So we're just doing a best first search. So remember, we're going to actually have our same picture we had before. So we've got our entire state space over here. Within that state space, we're going to have the start state, and we're going to have a set of nodes that are unclosed. Surrounding that set of nodes, we'll have a set of nodes that are open. And then we have states that aren't generated yet. And so again, just to be consistent with how I do my animations and how those animations are sitting on my website, we have in red here the closed list. We're going to have in green here the open list. And then we can think about any path that goes from start is going to go through the open list, and it's going to come out to, and this might be the goal, but really we can reason about any path that comes from the start state out to any state out in the world that we want to find an optimal path to. It happens to be the case, as Dijkstra's algorithm, the A star finds an optimal path to every state in the state space, not just to the goal. But hopefully it's going to be more efficient at finding the optimal path to the goal. Okay, so anyway, for now we're going to look at consistent heuristics, and then we're going to see what happens here. And in the last portion of the lecture, we looked at what it meant for the heuristic to be consistent, and we're going to derive that sort of in the backwards direction here for the sake of our proofs in this portion of the lecture. And so what we're going to do is we're going to look at a number of different properties. And so we have sort of a baseline property, which is like the 0th property, which is the, actually, well, we'll call this property 1. So what we want to say here is the F cost of all states, that when we run A star with a consistent heuristic, the F cost of all states is non-overestimating. And in particular, we're going to think about the start, and then we can think about what happens as we do this search to be just a little bit more precise. So the F cost of the start and other states as we expand them is non-overestimating. And we'll go ahead and prove this, but this is going to follow from admissibility and consistency. And so in general, this is true of the other states, but for the start, we can start with the start because we'll need that for sort of induction steps. And if we think about the start, well, the start is just the heuristic. The heuristic is non-overestimating, and so even here, it doesn't have to be consistent, but we know from the start state that we're going to be non-overestimating. And so that's sort of a baseline condition that we need. And what we get from this, so I want to call that 1A. Property number 1 sort of B, which is the main property one, is that the F costs and the G costs along any path, and actually we're going to say any optimal path, is an optimal path to any state, are monotonically increasing. Okay, so this is an important property because this is sort of the equivalent of what we saw for Dijkstra's algorithm. In Dijkstra's algorithm, the G costs were increasing because we required for potentially infinite graphs, we required that all edge costs have some epsilon positive cost to them. And so we want to see that, and that causes the path cost to grow over time, which guarantees that we eventually reach the goal with in fact, with the optimal cost. And what we're looking at here is that now we're going to introduce F costs, so which are G plus H, and we want to show that we have that same property. And so let's look at that property and see what we want. So what we want to have is that if, as we go from some state along a path, so let's just say that I'll show two nodes here, A and B. And the idea is if I go from f of A to f of B, I want f of A to be less than or equal to f of B. I want the f cost to increase. And here we're making the assumption that, that we are along the optimal path, that at least the optimal path to B. So as we go along an optimal path, and we go to A, we go to B, we could be going to some later state, but A and B are optimal. Then we want this property that our F costs are going to be increasing. And so in order to have this property, what we're going to see is we're going to break these up. So F of A is G of A plus H of A. And F of B is G of B plus H of B. Okay, so far so good, not much to say there. But what we can do is we can have the idea that the cost of B here actually is the entire path, which is the cost to get to A plus the cost to get to B. And so this is the point where we're assuming this fact that actually we're on the optimal path to B. So G of A plus H of A is less than or equal to, so we're turning B into the G of A plus the cost to go from A to B plus H of B. Okay, so that's what we want. And then here we now see that we have G of A on both sides. So I can say H of A has to be less than or equal to H of B plus the cost going from A to B. And this is exactly right here, the definition of consistency. Okay, so if we have a consistent heuristic, of course, if we run this the other direction, if we have a consistent heuristic, then along any optimal path, we're guaranteed that the F costs will increase and they will never decrease. Okay, so F costs along any optimal path are monotonically increasing. So they may stay the same and they may go up, but they're never going to go down. Okay. So if we have this property that, we're going to start with a non-overestimating cost, and then the costs are going to increase, and they're never going to go down from there, then we know in general we're going to have the F costs are never going to be overestimating. And so now we want to look at, and this is the same thing, I'm not going to write out this proof, this is the same thing as for Dijkstra's algorithm, is that a node, so if we're thinking go to any optimal state, some optimal state S, we want to pass from the start to any optimal state, then there's always going to be some state on the open list, is always going to be the open list with optimal cost until we close S. Okay, so a node on the optimal path to any state S always has, sorry, a node on the optimal path. Yeah. So a node on the optimal path. Okay, a node on the optimal path to any state S. Just make sure I get this right. Is always on open. Okay. So I don't know which node this is. Oh, sorry. Until S is closed. So we're saying if I'm trying to get to some arbitrary state B out here, it is always going to be the case that there's some node here on the open list at all times. And initially the start state is on open, and then you can show by induction each time we perform an expansion, then there goes a successor is going to be put on the successor. Every time you expand, the next state goes on to open, the next state goes on to open. And so there's always a state on open along this optimal path. Okay, and the interesting property that we want here, that we also have in Dijkstra's algorithm, but is a little bit more interesting here with a heuristic, is that every closed node has optimal G cost. Okay. And the question is here, is it ever the case that I could choose a node from the open list? So I could choose a node here and expand it before we found the shortest path. And the proof of this is nearly identical to that for Dijkstra's algorithm. So you can go back a couple of videos and look at this. But there's some properties here, a couple of properties I'll mention that make this, that ensure that this is true. So in particular, let's look at what would happen or what would require. So we say, suppose for instance, I'm going to expand some state here, which is on the open list, which is you know, on some path, but maybe I'm expanding it with the wrong G cost. So you can imagine here, I'll write this in red, that I found some suboptimal path to the state, and there actually is a shorter path that I found, or that I haven't found yet. And the key here is that if there is a shorter path, then what has to happen? Well, because we know from property 2, a node on the optimal path to here is always going to be on the open, that if I'm trying to expand this state right now, but it's not optimal, then there must be some other state back here which is on the optimal path, which is on the open list. And if we think about that state, we can break down for that state what is going on. So that state, right now we have, so if we're thinking about, imagine we're thinking about some state S. And right now it's sitting here with a G cost of G prime, which is too expensive, plus H of S. H of S is constant and never changes. And so this would be f of s right now. So we can imagine there's another state, which is a parent. So we'll just call it P, or it's some predecessor. And so what we know is that I can go, I have G of P. It's got optimal cost. So G of P is currently optimal. And then I have H of P. And so this is just equal to the f cost of P. And so this is the f, I'm going to call this f prime because it's the current cost of the suboptimal path that we found to S right now. And what we would see is that if we were actually going to try to expand S right now, given that I had a suboptimal G cost, what would have to happen? Well, if we couldn't expand it, then this state would have to have higher f cost than the current f cost I have right now. But if this state has higher f cost, then when I follow the path and go from P to S, then I'm going to find a shorter path to this state. I'm going to reduce this value, and therefore, because H stays constant, I would reduce the f cost of S. But we know that the f cost cannot go down as I go along a path, and therefore there's a contradiction here. Since the f cost can't go down, then there cannot be an f of P that's going to give us a shorter path, because that would require the f cost to go down, because the current f cost, since I'm not expanding it, the current f cost of P would have to be higher. Okay, so consistency basically says, yeah, I can't have a state here that is on a shorter path to S that I'm not wanting to expand right now, because of consistency is guaranteeing that this f cost has to be less than the f cost of the state that I'm eventually going to reach. Okay. And so what this tells us actually, so let's just say, oops, sorry. Property number 3a is that every state is expanded, every node is expanded at most once. Okay, because I'm never going to expand it with the suboptimal cost, therefore I must expand it with the optimal cost. And then the rest of the proof here actually follows exactly from the same thing we would see for Dijkstra's algorithm. So every node with finite cost will eventually be expanded. And the reasoning for this is that basically our F costs are always increasing. And so in Dijkstra's algorithm, what we had is the G costs were always strictly increasing. G costs could never go down and they could never stay the same. In A star, the G costs are able to stay the same because the G cost can go up and the H cost can go down and they can exactly neutralize each other. But the H cost can only go down a finite number of times before it reaches zero, at which point the G cost must go up. So this can only happen a finite number of times. And so the same reasoning here applies to as we have for Dijkstra. So eventually what we're going to see is that the F costs are allowed to stay the same for a finite amount of time, but eventually they must go up. And so then we could think about some other things that could happen. Could we ever run out of nodes on open? Well, no, because if a path exists, one node on that path will always be there. And so we'll always have, we're always going to be making progress to the goal. Could we expand states forever? No, we can't do that because the costs are always going up. And if we expand the goal, then we know that because every closed node has optimal G cost, that when I do expand the node, that it will be with a finite cost, and not only a finite cost, but with the optimal cost, and we'll do it in a finite number of steps. Okay, so I went through this a little bit faster than with Dijkstra's algorithm, but hopefully you can see that the same structure here is almost the same. If we have an inconsistent heuristic, then we lose property 3 because we could have nodes on the closed list with suboptimal G cost, and we also lose property 1 or 1b here because the F and G costs are not necessarily monotonically increasing. And so here it requires a more complicated algorithm because it says, well, I may find a shorter cost to a state unclosed and I could be doing many re-expansions, but we actually can prove that this will only happen a finite number of times. But I'm not going to sketch this any more detail. Okay, so this tells us that A star is optimal. So optimal with a consistent heuristic is what we showed here, or we sketched here. And so that's great. That's a nice property to have. And the question now that we asked, so before we looked at depth first iterative deepening, and as an uninformed algorithm, we showed that you cannot do better. And so the other question is A star optimal? That is, can we build a better algorithm than A star? And so A star dates back to 1968. And this was work that was done at Stanford by Nielsen and others, and they were doing this for Shaky the robot. They were looking at how can we do path planning and do it efficiently, and so they had this initial algorithm here in 1968. But what we see is it actually took until 1985 before we got the theory. So A star, 1968, 1985. There's a proof of A star in that paper, but there's actually complete theory was done in 1985, and this is by Decter and Pearl, Rena Decter and Judah Pearl. Judah Pearl, they were both at UCLA at the time. Pearl's still at UCLA, or I think he's an emeritus professor at this point now, and Rena Decter is at UC Irvine. And so this complete theory looks at all the cases, and there's quite a few cases that you can look at here, and really you could give a whole lecture that was trying to describe what's going on in those cases. And I'm not going to, in this lecture, want to go through all of those details, but I'm going to give one view of what we can look at. And this view will help us to see what is actually going on here. And the idea here is up to tie breaking, then A star is optimal, and then we really can't say much about tie breaking. And so their theory looks at, well, what are all the different types of tie breaking, and what are the many other conditions that are related to this? But what they showed basically here is that all nodes with f of n less than c star must be expanded. And this is sort of their main result. So all nodes f less than c star must be expanded. The nodes with f equal to c star may be expanded. And a really good way to think about this theory is, suppose you were given a path of some cost. And I asked you, can you verify that this is the optimal solution? And so the necessary expansions, and we'll come back to this in bidirectional search, the necessary expansions are those that are required to prove that a particular solution is the optimal solution. And so, of course, an actual algorithm, if it's searching, it's going to have to connect from the nodes with f less than c star to the actual goal. And how they do that is then an open question, and maybe there's some policies that are better than others or things like that, especially when you get to bidirectional search. But practically speaking, what we're thinking about is what are the nodes that are required to validate that a solution is actually optimal. So if I have a solution and I do everything, expand all nodes with f cost less than the solution, then I do know that that solution is the optimal solution. Okay. And so if we want to think about the optimality of A star, then we can think about a picture here. So suppose that there was an algorithm, and here we have this black box assumption that we have no additional information besides basically and I talked about this in a previous video, is we have no information besides the G cost, the H cost of a node. Like I can't look at the internal details and try and figure other things out. So what you can imagine is now I've given a problem and it's got a bunch of nodes, and I have to expand all the nodes that are less than C star. And the question is there another algorithm with no additional information, so an equally informed algorithm that could somehow avoid expanding one of those nodes? Okay, so we have the start state here. We've got this cloud of nodes that all have f less than C star. And then coming out of here, we've got the solution. And we're hypothesizing, of course, that it's C star. So suppose we had an algorithm that said, aha, there is some node here that I'm not going to expand, and I'm going to claim that I'm going to be both optimal and complete. So I'm going to find the optimal solution, but somehow I could do it without expanding that one node here that I wanted to avoid expanding. The question is, can we do that? And the answer is, if there was such an algorithm, then we could create a new problem instance. And then this new problem instance, what we would do is we could keep this goal, but all I'm going to do is I'm going to add a new edge here. So here's my new edge, and the new edge is going to go from this state to the goal. And I'm going to put here, a cost. Now, there's a couple of versions of how you want to prove this. For the moment, I'm basically going to say, well, I'm just going to put a cost of 0 there. Okay, so there's a state with f less than C star. And, or actually what I'm going to put here, sorry, is, it could be 0, but what I'm going to, if I call this node P, then this state is going to have a cost of H of P. Okay, so, and there's one little detail here I'll just cover in a second, but what we see here is in this new problem that is otherwise identical to the other problem, this algorithm that avoided expanding this state, it's again going to avoid expanding this state, but that means that it's going to miss the fact that there is a solution here. So on the previous problem, we found a solution of cost C star. On the new problem, whatever C star was on the old problem, the new problem is going to have a lower C star because the state has f less than C star. And here it is, whatever the G cost is plus this H cost is going to get us to the goal. Okay. Now, suppose, though, that I insisted that every state have a heuristic, I allowed states to have a heuristic of 0, but I know that all edges must have at least an epsilon cost, then this might require me to have an edge cost 0 here, and maybe this is going to violate things going on. And so here, in that case, there's a couple different ways you can deal with that. You know, you could allow 0 cost edges as long as we know that, that the graph is finite. If we want the graph to be infinite and we require some epsilon, then what we could require here is that all nodes in the state space must have a heuristic of at least epsilon, except for the goal. And that would mean that we could always construct this case where we would be able to put an epsilon here. And of course, that would be a correct heuristic. There'd be no reason not to give every state a heuristic of epsilon if we weren't, for the case where if we're not the goal state. Okay, so this idea here, and we'll see this proof again when we come to bidirectional search, but the idea is that we could take a problem instance, we could duplicate that problem instance, create a new edge to the goal, and we basically create a shorter solution to the goal if there was any node that some algorithm that some algorithm avoided, and therefore that algorithm would not be an optimal algorithm. It would not find the optimal solution, and therefore any optimal algorithm. And so the language in this is a little bit confusing because what's been used, if you go back to the original A-star paper, is they call it an admissible algorithm. An admissible algorithm actually doesn't have anything to do with whether the heuristic is admissible or consistent. But it's talking about the algorithm means that it finds an optimal and that it finds an optimal solution if a solution exists. And so so any optimal algorithm must expand all states with f less than c star. And so there cannot be an algorithm that's better than A star in that regard. Now there's other measures we could look at. We could talk about maybe how many states are generated, or we might want to talk about how many times states are generated or expanded. And so on those metrics, we'll maybe get a chance to talk about some of those, at least in terms of expansions that we can't do better. A star with an inconsistent heuristic may re-expand states. And as I said, we'll get into all those details in a later lecture. And so that gives us basically an overview of A star. That A star is for a unidirectional search algorithm. So the only thing we give is the ability to search forward for a fixed, fixed heuristic that we're providing to the algorithm. So you get no other additional information, then no other algorithm can do better, with the exception of tie breaking in this space of where I need to go from those states with f less than c star to actually getting to the goal. And again, there's these theoretical conditions look at different cases of like, well, what if the goal is always exactly next to this region of states with f less than c star? What if it isn't? And what are some other things that we could compare and look at there? Okay, so this is the A star algorithm. And again, it's just a best first search. So we just take the state with best F cost, we expand it repeatedly. And if we find a shorter path to a state, then we update that. And when we do that property, we're able to find optimal solutions. And this is an optimal unidirectional algorithm. We cannot do better than this in terms of the node expansions that we do. Of course, we can have data structures or other things to go faster if we know different properties of our state space. But yeah, this is the venerable A star algorithm. And what we're going to be doing is then looking at things that we can do to improve it in the future. And we'll look also, so A star, sorry, the other thing I didn't say, what is the space and time requirement? And the space and time requirement is it has to do exactly the number of nodes, at least the number of nodes that have f less than c star. And so this might be b to the d or b to the d minus 1. I mean, depending on where you're counting this exactly. In an exponential state space and a polynomial state space, it might be r cubed or r squared, depending on the dimension of the state space. But it has to keep them both in, it's going to have to expand them all, and then it has to keep them in memory because A star does keep everything in the open list. And so in the next video, what we're going to be looking at is we're going to look at, well, can we do an equivalent of depth first iterative deepening, except now using these heuristics and using f cost as guidance? And the answer is, of course, we can do that. But just one last thing here I want to be careful to say is, although A star is optimal with a consistent heuristic, when we give it an inconsistent heuristic, it is not necessarily optimal. And so that's an important thing to be aware of. And just for the fun of it, I'm going to show a couple of videos here. And the goal of these videos is just to illustrate some other things that we might want to pay attention to when we're thinking about our implementation of A star and how it works. Okay, so this is a search problem. We're searching from the upper left-hand corner, which is the yellow state up there, the little yellow circle. And then we're going to search sort of to the bottom middle of this problem. And I'm just going to show you some things that can happen here. So the first problem we're searching, so this is a problem in an 8-connected world, so we can go in 8 different directions. And the first thing we're going to look at is what happens if I use a straight line distance as a heuristic. And when we do that, what we see here is that we are doing quite a few node expansions, and we're not actually going directly to the goal. And so what's going on in this case? Well, what's going on is eventually we're going to get down here to the goal, but we've done a lot of work in doing this. And the issue here is that this heuristic thinks that maybe if I go one node in any particular direction, I'm then going to find an edge that's going to take me directly to the goal. And therefore, this discrepancy between our world being an 8-connected world and having these sort of straight line edges that go directly to the goal mean that I'm going to have to do a lot of work actually because of that discrepancy. Now we can fix that discrepancy by using a heuristic, which is called octile distance, which basically says, yeah, I'm going to go diagonal some distance, and then I'm going to go cardinal some distance. And if I do that, then this can actually give me a perfect heuristic in this domain. But even using the perfect heuristic, if we're not careful, we could get behavior that looks something like this. And all this is an issue of tie breaking on the open list. So I can have a bunch of states on the open list that all have exactly the same F cost, and then I have to ask the question, well, given the same F cost, how do I choose which one to expand first? And it ends up that in this case, what I'm expanding is low G cost first, but I could also expand high G cost. And if I expand low G cost, what you can see is that the search, I just run this again, the search is prioritizing states that are very early in the search. And what's actually going on here is all the states that we see expanded here all have exactly the same F cost. And so we actually do almost as much work with this heuristic as we did in the previous case. But if we change our tie breaking to break ties towards high G cost and low H cost, and that essentially says low nodes that are very close to the goal, they have high G cost and low H cost. So we're trying to get as close to the goal as possible. On the exact same problem, then the amount of work we do now is very small, and we actually go directly to the goal and don't expand any extra nodes besides exactly the optimal path. So this gives us really good performance. And so this is something really important in practice. Is very often the case that we want to expand nodes from low G cost to high, or sorry, from high to low. That is when I have the same F cost. I don't want to. I'm of course have to expand the low G cost first to get to the high G cost, but I want to basically push out as far as I can with the hope that I'll find an optimal solution early. And in this problem, what these really are is these are all the states with F equals C star. So here, all of these states, sorry, go back one more step. There, all of these states have F equals to C star, and this is the effect of tie breaking at the last layer of the search. So if we do that wrong, if we're not trying to sort of be aggressively getting to the goal at the last layer, then we might end up doing a lot of work in that last layer. Versus if we are trying to sort of minimize that size of the last layer by going aggressively through that, then I'll get to the goal very quickly. Okay. So that's what we're doing here with A star, and that's just a note on the implementation. And we're going to continue to look at other algorithms. We'll look at what we can do with sort of the depth first search version of this, which is IDA star, in the next video. And then we're going to go back and start to look at what are the worst case behaviors of these algorithms, and then how can we start to fix those in practice.